Hi, good afternoon, everyone. My name is Eveline Baens, and I'm a junior researcher at the Soil Service of Belgium. And today I'm here to introduce all of you to the Carbon Agroforestry tool, also abbreviated as CARAT. This tool was developed by the Soil Service of Belgium, ILVO and Fornalab. So this tool was actually developed to simulate and to visualize the spatio-temporal variation in carbon stocks, the above and below ground carbon stocks of agroforestry systems in temperate Europe, and this over a time period of 30 years. So today I'm going to give some information about the calculations that went into developing this model, and also give you a look into how the tool looks like in its online web application. So CARAT consists of three main components. We've got firstly the leaf fall distribution model from Verheyen that will quantify the annual leaf fall of the trees. Then next, the carbon stock in that plant material will be estimated using species-specific allometric relationships and growth data from literature. And then this data will then be used in the Roth-C model that is used for the conversion of the organic carbon in the topsoil of non-waterlogged soils and agricultural plots. So this will then be used to calculate the carbon that comes from the leaf fall, and that will be incorporated into the soil. But the model also takes into account the above ground woody biomass, and this will be calculated again by using species-specific allometric relationships. So this is the homepage of the tool that you will see. It has 4 different tabs, 2 where you will have to give some input from data that you collected yourself, and then 2 other tabs will give you the output of all the calculations. So the first tab, the field, here you will define your field dimensions, the tree species, and the configuration of your trees in your field. The second tab, there you can define some additional soil parameters of your agricultural plot. Next, the raster output. So here, the leaf litter fall distribution and the soil organic carbon that was calculated by the model will be displayed here. And lastly, you've got the summarizing table where you will get your field level estimations of all the calculations. So firstly, the field design, you can choose your field dimensions in 2 different options. You can give the size of a rectangular field. So here I chose a 30 meters by 30 meters plot, and a raster will be generated with those dimensions that will represent your field. The other option is that you can search your field on the map. So you can zoom into the map and actually select your field, and then those dimensions will be transferred into a grid. In the next step, you will select your tree species. At the moment, you can choose between 19 different tree species. And if the one that you're interested in is not between all of those, there's also the option of a sort of standard tree. And this has the characteristics that are an average of all the other different tree species that are present here in the tool. For this example, I chose apple trees, walnut trees, and poplar trees. You can place your trees into the grid in 2 different options. So you can opt to create a grid of trees. And for this, you can define the vertical and horizontal distances between the trees, and a grid will be generated. As you can see here on the right by the yellow trees there. So those were the apple trees. And then for the walnut and the poplar trees, I chose a random location. So you can also place your trees by just clicking on the desired location inside the grid, and they will be placed there. So next, I will give some information about calculations. So as I said, the carbon stocks in the above ground woody biomass will be incorporated into the model. And to calculate these, we use species-specific allometric relationships that are based on the diameter at breast height of the trees. So we will model the DBH per tree, and as input for that logistic regression, we use species-specific parameters based on literature data that we found. And this equation also takes into account the age of the tree. So the DBH will be calculated for each tree species that you use, and this for each year, because the model makes calculations over a time period of 30 years in total. Then next, this DBH will then be used as input to another set of species-specific allometric relationships that will model the tree's above-ground biomass as the trees grow throughout the years. And then to calculate the carbon stock that is present in that woody biomass, we used a conversion factor of 47%. So this then gives you the total carbon stock that is present above ground. Then in the next step, we will take into account the carbon stocks that are present in the leaf litter. For this, we use the leaf fall distribution model from Vanneste, and this model estimates that the amount of leaf litter decreases exponentially with the distance to the tree. Other things that it incorporates into the model is, again, species-specific parameters. So it's different for each different tree species. And the diameter at breast height is also incorporated, and that is calculated like I explained in the previous slide. So after that, we got the amount of leaf litter. But we still need to know how that will be incorporated into the soil. So as a next step, we will use, again, the conversion factor of 47% to calculate the total organic carbon content in that leaf litter. Then the method of Belt et al. Will then be used to divide that organic carbon into different fractions. And with those fractions, we get the TPM over RPM ratio, and this gives you an idea of the slowly and rapidly decomposing plant material. And this is then used finally as inputs to the Roth-C model, and this eventually then gives you the evolution of the soil organic carbon content due to your leaf litter fall. So then we will then go back to our online interface. So in the next step, you can define some additional soil parameters that will be used as input of the Roth-C model. Also, you can define here if it's arable land or grassland as additional parameter. Okay, then what you can see here is the first type of output that will be generated. So the top figure on the left, you can see the representation of the soil organic carbon content throughout the years, throughout the 30-year time period. The blue line here is the conventional system, and the agroforestry system is represented by the red line. So the upmost left one is at a distance of 2 meters from the tree, and then when you go to the right, you've got a distance of 5 meters, and again 10 meters after that. So you can see you've got an increase in soil organic carbon content, but that it decreases as you go further from your trees. At the bottom, there is actually the same represented, but there the carbon content is divided into different fractions. Okay, so the next slide is the spatiotemporal variation that is represented. So first we've got the leaf litter fall distribution. So here I showed it for year 1 to all the way to year 30 with 5-year increments. So here the legend is you've got a light brownish color going to darker green as there is a higher leaf fall throughout the years. So you can see that from year 1 to year 30, there's an increase in leaf fall as the trees will grow and they have a bigger canopy. Also, you can see a difference between the different tree species. Like here, you can see the poplar trees and the higher litter fall than the walnut. They have less litter fall. Then the next slide, here you can see the output as soil organic carbon content that will increase throughout the years, again, from year 1 to year 30. And a darker color represents a higher soil organic carbon content. So again, here you can see the differences between the different tree species throughout the years. This gives a similar output, but this is solely the increase due to the leaf litter fall. So the previous slide was the total soil organic carbon content each year, and the next one is the increase. So as you can see, as the trees grow, the yearly increase in soil organic carbon content due to leaf litter fall also increases. The last type of output is your field level estimation. So what you are given here is the increase in soil organic carbon content due to your agroforestry, the total carbon in your trees, and the total carbon increase in your entire field due to your agroforestry. And this will be given for your field, but also per hectares. And this throughout all your years from year 1 to year 30. And also it is represented in a nice figure. Okay, so currently, we have developed a nice model, but it must be said that there was a lack of in situ data from actual agroforestry fields. So there is some data that was incorporated into the model, but it's still quite limited. So because of that, there was a limited parameterization and validation of our model outputs, and some assumptions and generalizations had to be made because of that, which can affect the reliability of the model. So of course, our logical future steps are validation and calibration with in situ measurements from actual agroforestry fields in temperate regions. So this will include leaf fall, the DBH, and soil organic carbon measurements. Also, some things we would like to incorporate in the next couple of years is the effect of the tree species on the actual crop development. And a broader array of crop rotations and fertilization practices. And an important point for us is also the accessibility for the tool. We want to reach as broad a public as possible with our tool. So we would like to further increase the user friendliness if possible. So hopefully I piqued your interest with my explanation. So where can you find this tool? Well, you can find it on the website of Agroforestry Vlaanderen at the Agroforestry planner. So in the same research project, we also developed other kinds of tools that concerning agroforestry, like and also quite interesting cost-benefit tool called Impact. But the CARAT tool, you can also use like at the right top, you can use a QR code or the website link. We also made an English manual about the use of the tool, so which can also be quite interesting, and a video on how to use the tool. So CARAT in a nutshell. It quantifies the long-term carbon storage in your tree biomass and in the soil. There's a broad range of options that you can use as input as a user, like the species choice, your field design and soil conditions can be defined here. A wide range of applications can be possible, like there's potential for carbon credit valuation for the farmers through agroforestry implementation. And it's quite easy to use the tool, so no computational expertise is necessary to actually use it. I would like to thank you for your attention.